That AMPA book contains a sort of short version of this talk filled with embarrassing misprints to the author. You might buy the book just so you can have the exercise to find the misprints. Let me see here. Okay, so this talk is about Majorana fermions and some generalities that I'm fond of. And I'm going to begin with talking about the square root of -1 as a clock, as an oscillation. You will see this in the form of a little fable that I'm going to tell you. So my fable begins with the statement, God does not play dice. And let me read the fable to you. This, by the way, is something that I found on the internet when I was doing a Google search for a Schrödinger's equation. I kind of like it. Here's a little story about the square root of -1 and quantum mechanics. God said, I would really like to be able to base the universe on the diffusion equation. But I need to have some possibility for interference in waveforms, and it should be simple. So I'll just put a plus or minus ambiguity into this equation like this. This is good, but it's not quite right. I do not play dice. The plus or -1 equation will have to be lawful, but not random. Nothing is random. What to do? I shall take plus or -1 to mean the alternating sequence. And time will become discrete. And then the equation will become a difference equation in space and time. That is, here's the space, the time difference is equal to, and then I have -1 to the t, where t is the t for time, 1, 2, 3, 4, and so on for time, kappa, that same constant, times the second difference here. And I've eliminated, for the sake of display, the things that I should be dividing by, so that I have the second difference in x is equal to this gadget here. That'll do it. Then I have the plus or minus ambiguity written in a lawful way, but I have to consider the continuum limit, and there's no meaning to -1 to the nth time or the tth time in the limit, in the realm of continuous time. What to do? In the discrete world, my wave function, not a bad name for it, divides into psi even and psi odd, where the time is either even or odd, so that I can write that the time derivative of psi even is kappa second difference on psi odd, because it should be time, and the time derivative on psi odd minus kappa, because you switch the sign, psi even. And I'll take the continuum limit of psi even and psi odd separately. I'll call this the Schrödinger equation. Instead of the simple diffusion equation, I have a mutual dependency where the temporal variation of psi e is mediated by the spatial variation of psi odd, and vice versa. This is the price I pay for not playing dice. So now, if we write this in the usual form, we can use I, and write psi is equal to psi even plus I psi odd, and then dt psi even equals second difference odd, and dt psi odd equals minus second difference psi even becomes I d psi dt equals kappa d squared psi dx squared, where psi is written in the usual form with I squared equal to -1. So finally, a use for that so-called imaginary number that Merlin has been bothering me with. You might wonder how Merlin could do this when I've not created it yet, but after all, I am that I am. This line has the property that I squared equals -1, so that it switches in this way, and I equals -1 over I, so you see that if I equals 1, then I equals -1, and if I equals -1, then I equals 1. So I just spent its time oscillating between +1 and -1, but it does so lawfully, and I can regard it as a definition that offers the ambiguity of plus or -1. In fact, I now see what Merlin was getting at. When I multiply I times I get -1, because the I takes a little time to oscillate. And so by the time the second term multiplies the first term, they're just out of phase, and we either get +1 times -1 or or minus 1 times plus 1, and either way, I squared equals minus 1, and we have perfect ambiguity. So now with the Schrodinger equation, I'm telling the story again in this slide, that's all. I can write, having created I, A plus BI, and then it switches accordingly, and the two equations become one equation, and we have the Schrodinger equation. So this means that I can start with a discrete version of the Schrodinger equation where it looks like the diffusion equation recursion, except that the signs go plus minus, plus minus, plus minus in this way, separate into even and odd parts, and land on the Schrodinger equation from the diffusion equation. In other words, at the level of discretizing it and putting in the correct entities here, you have the minus 1 to the t, and the recursion for the wave function is given this way with the minus 1 to the t. Without the minus 1 to the t, it would be looking like the diffusion equation. So that's the first part of the talk. The square root of minus 1 is a clock. Comments? All right.
Did you say a plural?
What?
Did you say
where was the question?
Here.
Yeah.
Did you say it was a? I heard you say it was a frog.
A clock.
A clock.
I hear all sorts of things. Yes.
I have a suggestion.
Yes.
E to the I is also a clock,
Certainly.
and that may be a.
E to the I theta
Well,
equals
yeah, right.
cosine theta plus I sine theta, and that converts the discrete clock to a continuous wave, as we all know. Right. And so, those are not unrelated to one another at all. Right. But then,
So
if you
this
think
sounds
about
like
it a
you're-
little further,
you're
the
quantizing
discrete,
E to the
I'm
I.
sorry, we're talking at the same time. Go ahead.
Well, it sounds like an alternative way of approaching this is to start with E to the I theta and discretize it. And you get the wave becomes a square function, and you get a plus minus, plus minus, plus minus.
How does the wave become a square function? You mean like use a Fourier series and get the square wave back? That's fine. There are lots of ways to go between the continuous and the discrete.
Sample it.
I'm sorry?
Sample it.
Sampling, fine. I tend to avoid statistical things, but sampling is fine. But I like to think about how you go back and forth between the continuous and the discrete, because ultimately when you're doing mathematics, it's all discrete, it's all language, and then you have managed the language in such a way to have concepts of continuity working with you mellifluously. Yeah.
Can you, one question for you. Can you explain, what was my asking, how does this relate to can you say this as a norm, x times x equals minus 1? How does that relate to the norm concept?
No, I didn't get
How does
the
it
word.
relate to the norm concept?
The norm?
Like x
I
times
mean like
x?
z bar is
Yeah.
the norm squared of the complex number.
Well, like x times x equals minus 1 will give you the imaginary, and x times x equals 1 gives you the real. How does that relate to, or is this completely independent of that?
Not at all. Where you might take your question to be where are the conjugates, because the
Right,
norm,
yeah.
from the point of view of complex numbers or such numbers, comes from multiplying the number by its conjugate and taking the square root. And here are the conjugates. I mean, in this point of view, if we go into it a little further, the square root of minus 1 is thought of as an oscillation. But then there are two ways to look at that oscillation. Either it's in phase minus 1 to plus 1, or it's in phase plus 1 to minus 1. Those are the two conjugates. And then how am I going to take care of that last phrase of, I think of multiplying this, I think of multiplying the ambiguity by itself and getting minus because there's a phase shift that happens. I want to formalize that. I will. It'll come up. Okay. The other thing that is implicit in this slide is the idea that it looks like a paradox. That is, it looks like A is equal to not A, where that means not, or G is equal to not G. It looks that way, and if you were trying to figure out what it meant before the 1500s, you might say, well, I'm trying to solve this. If I is equal to -1, then that says I equals to +1, so it doesn't work. It's a paradox, right? On the other hand, there's a recursion involved, and the recursion, of course, played out in time is the oscillation. So if you started with the contracted paradoxical point of view, then it will display as an oscillation when you try to make it work. On the other hand, when you have the form of a recursion, it could be a fixed point, but I'll come back to that.
Another question?
Yeah.
How do you feel about extending the I clock to knot theory or topology? Simplistic example, overcrossing, knot shadow, undercrossing, iterating to that. Is that, do you find that possible extension of this model?
Well, I will come to knot crossings.
But can you apply the I clock to that?
And one could think of recursions in relation to knot crossings or weavings. Certainly one can. I think you may have something else in mind there.
I do,
So we
but
can
that's
talk
why I
about
was-
it when we have the time to talk about it.
This is the last question, I'll let you continue with the conflict. Can you think of the logical not operator as a sort of clock, or is it ever making correspondence that shouldn't exist?
So yeah, I'm thinking of the logical not operator as something that's just ticking, causing the tick. It's whatever makes the gear turn and tick the clock, if you like. Okay. So then I want to mention a philosophical point, which I'll come back to. This is about the not operator. Wittgenstein had a lot of things to say in the Tractatus. One of the things he said is that, however, the signs P and not P can say the same thing is important, for it shows that the sign not corresponds to nothing in reality. And he said, how can all-embracing logic which mirrors the world use such special catches and manipulations? Only because all these are connected into an infinitely fine network to the great mirror. And this is in back of, or poetic speech in back of his picture theory of reality in the Tractatus. And of course, later he rejects the picture theory of reality, and implicitly in rejecting the picture theory of reality, rejects perhaps this notion that the sign not corresponds to nothing in reality. Somehow the mirror and the reality are coming together later for him in practical terms, where the meaning of the word is its use, and the words are part of the reality, and they aren't just mirrors. That same thing is in back of, whoops, sorry. Oh my goodness, I must be pushing entirely wrong buttons here. Way down at the bottom of the slideshow. Okay. You just saw parts of the slideshow that I didn't intend you to see. Oh, yeah. So, not in Spencer Brown is this mark here. So that's just a sign for not. But I'm going to be speculating that the sign for not could be thought of as a particle, and then at the level of description it becomes a possible element of reality. And in any case, Wittgenstein's provocative question about could the negation sign be an element of reality is worth thinking about. And then the limits of my language are the limits of my world, and the subject does not belong to the world, but is a limit of the world. And all these statements are statements which we tend to reject in some form, partly reject. Does the subject belong to the world, or is it a limit of the world? Maybe you would prefer the subject to be belonging to the world. So I wanted to just go back to that as some thoughts in back of And now the slideshow gets a little harder to read because I started thinking about all this again when I was preparing it, all too near the talk. And so found myself writing a set of notes which I thought were better than my slides, and photographing them with my computer camera here. But I think you can probably read this. I'm thinking about a distinction a la Spencer Brown at the beginning of this organization. The mark stands for a distinction, and it is a distinction for an observer of the page. Of course, as a physical mark on the page, it makes no distinction, but the observer is willing to regard this as the inside and that as the outside, and to place an imaginary boundary along the bottom to form a full square or rectangle that constitutes the distinction between inside and outside for that symbol. The symbol doesn't acquire its meaning as a distinction without being correlated with an observer. And then another principle is that a thing is identical with what it is not, a logical principle. And this is particularly the case when you're thinking about things that are created by your observation. Then to the extent that you know the inside, you know the outside. If you explore the inside to the highest possible degree, then you know at least the shape of the outside quite well. And you can take this and wonder whether it answers Kant's question or not about the Ding an sich. We take the form of distinction for the form, and then these are quotes from Spencer Brown. And we now see that the first distinction, the mark and the observer, are in the form identical. So in that view, a distinction comes along with an awareness, and that awareness actually is the distinction. The distinction is not this mark on the page. The distinction is the entire circle of awareness that is creating the distinction that you mean when you see the mark. So I bring all this up not to introduce you, not just to introduce you to a notation, but to remind you or introduce you to a point of view that would start by thinking about the world and thought in terms of perception, similar to Wolfgang's talk, but not exactly in the same framework. Yes?
But you used the word circle of awareness. Can you repeat that sentence?
I don't know if I can. I said that there is a circle of awareness that encompasses the apparent observer who is apparently distinct from the mark, and the mark which is observed by the observer. And in the presence of that circle, there is no distinction, and there is a distinction, right? It's a paradox, but it's a common enough paradox. You are the world, you are not the world.
Yeah.
Could that be kind of like an arbitrary duality that acts as an idempotent?
The mark acts as an idempotent, and we'll come to that. Where are you? Yeah.
Are you talking kind of sort of an anthropic principle kind of thing where it has its property because it's human beings are looking at it, or?
Well, the anthropic principle is a large-scale version of that idea, which I'm thinking about in terms of the simplicities of looking at a mark on a piece of paper. But in the anthropic principle, the universe is shaped so that the observer can observe it, and the observer is shaped so that he or she can observe the universe. And one takes that principle seriously and tries to see it in physics and natural science, right? So, right, you agree with me that that's some sort of expression of the anthropic principle, otherwise we're not talking?
Yeah, that I would definitely say so. I've always been a bit skeptical of the anthropic principle.
Oh, we can be skeptical of it, for sure. But then, in terms of our own, it depends on how, do you want that to go all that you would like that if you're going to use it to go all the way down to the details of physical law and physical constants and
Right.
such things. But then hardly anybody argues about this sort of circularity of shaping us and our worlds in terms of our perceptual worlds. So it's interesting, it's important, I think, to go back and forth between what you understand directly and what you might conjecture in the large. Right?
Yeah, okay. Well, here, yeah, I should let you go on that.
Okay. So we begin in the realm of sign and symbol, and with the understanding that any apparent distinction is accompanied, the equivalent to an awareness of that distinction. Signifier, signified, and interpreted in Peirce's terms arise simultaneously. Awareness and the distinction arise simultaneously. The sign, the mark, refers to itself in the Spencer-Brown case. And by the way, Peirce also devised a calculus, whose name I forgot just now, which is essentially equivalent to Spencer-Brown's calculus. Somebody remind me what
Semiotic. Semiotic.
No, never mind. Anyway, he calls it something, and it's essentially equivalent to a calculus of distinctions. He uses circles, and he worked out quantifiers for that calculus as well, and does logic using it. The only difference, if you look it up, between the Spencer-Brown calculus and this one is that and or are switched, as they often are when you start down a Boolean line and you end up with and or being switched one way or another. It doesn't change the real structure. Mark but this mark making a distinction refers to itself. And so we could write mark, arrow mark, where this is an arrow of reference. And in fact, we can write the mark is the that which is referred to by the mark. That is to say, the mark solves the equation x is equal to what is referred to by the mark. Just as I can say, I am the one who says I solves x is equal to the one who says x. These fixed points are eigenforms or fixed points, and Heinz von Forster spoke, it was a cyberneticist, spoke of objects as tokens for eigenbehaviors. And this is a point of view about objects which is worth injecting into the quantum dialogue or metalog. You can ask, what do you mean by an object? And you can take as an answer that it's a token for an eigenbehavior. That an object, and that talks about the object as how the symbol arises, doesn't say how it arises, but it is the eigenform that you're looking at. You're looking at, whenever you look at any object, a glass on the table or another person, you're looking at some kind of invariance under some transformation, which is leaving that the same again and again in your perception. So it becomes a token for an eigenbehavior, and that is a way of thinking about objects.
Can I ask one quick question?
Sure.
This wonderful statement, I'm the one who says I, from my point of view, that redefines I within the sentence. Is that what you're talking about in terms of the whole thing?
In other words, backwards without disturbing that. Yeah, it's good. Okay. So I wrote, I am the one who says I, and you asked.
I said that means that the system that produces the product is equal to the system which redefines I. I, the system, produces something, but the I in the beginning of the sentence and the I at the end of the sentence refer to different things. One is the system, the other is the product that the system is producing.
That's certainly a valid way of thinking about it. I like to think about it that way. I'm a big observing system, and I have the capacity to make references, and I can even make references to myself having become an object. But then I'm referring at the beginning, there's the big system, and that at the end of that line, there is a pointing to a symbol for that system. So I could stand for system at the beginning and symbol at the end, if you want to interpret it that way. And then when you speak colloquially and say, I want to have lunch now, you're referring to the whole thing, right? You're using the symbol and you collapse it, right?
Right.
You keep talking about I. And furthermore, in this way of speaking, which is highly evolved, the I could be anybody, and so that I doesn't refer to any particular person. It just attaches itself to the speaker because the speaker is such a system and is willing to take the I on.
If you distinguish, if you put a little mark on one of the eyes,
Yeah.
distinguish it between.
Yes, I could, but we don't in language, do we? So,
Oh, I know, but
so that's one of the funny things that goes on. Let me elaborate on that.
Okay, sorry.
No, but I like this point. Let me elaborate on it for a moment. One of the things that happens is that you meet somebody. I'm talking about naming, but I want to say in terms of people. I meet you, and Richard says, "This is Wolfgang," and I say, if I'm awake, I say to myself, "Wolfgang," and I put it with your face. And the next time I meet you, if I'm not in a senior moment, it's Wolfgang right there, and not "Who's this again?" Although that happens sometimes, right? So what happens is that when you meet someone, the name is here. Here's Wolfgang, the name, and the object, Wolfgang, the person. And then a shift occurs where the name, the symbol, is shifted across to the apparent object, so that this becomes person Wolfgang over here and stays that way. It's over there. And this is true of every object that you have in the space. You look at a chair and it's a chair, it's not an unknown thing. Picture on the wall, and all sorts of things are projected out there onto those objects by these shifts that have already occurred cognitively.
Yeah.
That shift from A refers to B, to A with a little mark on it refers to BA, where A is sitting over here. It's happening all the time, and we don't put a mark on the meta name. My name for you, Wolfgang, is a meta name, except when it's occurring with you, and then it's just your name.
Right.
So over here in my cognition, I have this big list of meta names, but they're marked somewhere maybe, but they aren't marked in my speech. The speech is collapsed. Maybe they're marked in some Chomskyan deep structure, if you believe in that kind of thing.
Well, I think
So-
our theories
so I
are
wanted
very
to-
similar if we add the little mark, as I separate.
Yeah.
Great.
And that shift is exactly Hegelian in the sense that it's the same, that trick, which we do all the time, is exactly what generates the Hegelian self-reference, but that's another talk. I mean, that's more talk. All right. So I'm concerned with this question of what is left unsaid, or what is left unmarked in the language. But it's important that things are left unmarked, because if you started putting markers down for every single thing that happens, everything would be festooned with so many reference markers that you wouldn't be able to move. So we don't do it that way. And even with Spencer Brown's mark, I prefer to just draw the mark and think conceptually it refers to itself, rather than draw an arrow and separate it into two parts and so on. It's practical not to write everything, and yet you would like to write everything. And when you go to formalisms, then you feel the need to put a lot of things out there in formalism that you wouldn't have done otherwise. I'm sorry, it's over talking. Okay. Another example of eigenform in language is this sentence has 33 letters. This sentence has X letters, and 33 in this form solves the problem. It refers to itself under those conditions and is true, if you count. So a process can fit into itself and becomes an object. How it becomes an object for cognition, I don't know, but it does, right? And scientific results are eigenforms, approximate if you wish. It is the self-fitting that is important, not the question of the external reality. So that when you get a good scientific result, it means that something fits, and it can be seen to fit by all the different observers. And it isn't a question of whether there was one of those outside. In the formalism of a transformation, E is equal to f of E. And under the widest circumstances, any f can produce its own fixed point. This is a very wide circumstance. I could make a fixed point for f by simply iterating f on itself forever, whatever that would mean, and then you do one more f and you get E back, as in a nest of boxes, and I put one more box around it and it doesn't change. That's one way, in the most widest of circumstances, to get a fixed point. Or I can do the following. In a domain where things can act on themselves, and new entities can be defined by writing down equations involving interrelationships of the old entities, and I'll call that a reflexive domain, then you could write G is defined by G applied to X is f of X applied to itself. And then, you see, fixed point. Because if G applied to X is f of X applied to itself, then G applied to G is f of G applied to G by substitution. So fixed points always exist in a reflexive domain. But when we're in ordinary language, we are in a reflexive domain of a certain kind. And so references and self-references can occur. And this is skirting the edge of paradox, because we could take Wittgenstein's notorious negation and put it right there. And then this would say G is equal to the negation of itself. And you would have a fixed point for negation. But negation is not supposed to have a fixed point. It's Russell's paradox again. So you have to take care if you don't want that to happen. Now, in the calculus of the mark, there are two equations. Two equations. The mark next to the mark is equal to the mark, and the mark over the mark is equal to nothing. These are understood in the following way. The first one is said, the value of a call made again is the value of the call. That is, each mark is the name of the other mark, and can be said more simply, in that the mark is the name of itself. So each mark is the name of the other one, and one of them can be eliminated. The value of a crossing made again is not the value of the crossing. Crossing from the marked state is the unmarked state. There's one more equation which I didn't write, which would be mark equals mark, where the two marks, just like the two I's in the discussion with Wolfgang, means something different. Mark equals mark, but the first one means cross from the unmarked state. And the second one is the marked state. Name and process are either equal or not equal, depending on how you think about it. The mark is both a process, crossing from, and the name, the symbol for that process, and mark equals mark is like I am the one who says I, indicating them both. Now the mark is a kind of logical particle with two ways of interacting with itself. And just for the sake of reference here, this is how you build the ordinary first-order logic with it. You take the mark itself to stand for true, and the unmarked state to stand for false. And then negation is given by crossing, juxtaposition is or, A cross B is A implies B because it's not A or B, and A cross B cross all is not the or of two knots, which by De Morgan's law is and now you have ordinary logic, and and then you can do calculus of logic with this, and it's often convenient. So the mark is a logical particle that can interact with itself to produce itself or annihilate itself. Now let's switch topics. A Majorana fermion is by definition a particle, an abstract mathematical particle, or perhaps a real particle, that is its own antiparticle. It can interact with itself to produce either itself or nothing. Radiation, however you want to think about that. And the nothing can interact with the particle to produce just the particle or nothing. The mark as a logical particle is a Majorana fermion. P squared equals P plus star can be regarded as the fusion algebra for the mark. That is to say, P interacting with P produces P or nothing, and you can write it algebraically by writing a list of possibilities in that way. And in this case, it's a well-known quadratic equation, which is related, if you were to solve it as P squared equals P plus 1, you would find the golden ratio and Fibonacci numbers coming out. And as a result, certain physical models related to Majorana fermions are called Fibonacci models. The creation annihilation algebra for Majorana fermion is more subtle. Next slide. But we can draw a picture, we can look for iconic pictures. If you think of a little string, not string theory, but a little string interacting with another little string in the usual surface diagram, then you see that two adjacent strings go through a saddle point and end up at a single string. That's the particle interacting with itself to produce itself. Or concentrically, two strings like this go down through a surface where the critical point is now a line, a circle of critical points, so it goes down to one circle and disappears all at once. And that's two concentric circles canceling, and that's the other equation with the mark. So if you like the geometric form, concentric or adjacent circles becomes the same as the Spencer-Brown or Peirce kind of calculus. Now I want to recall something about physical algebra. Recall the creation and annihilation operators for fermions. Now, if you're a naive learner of quantum field theory, it seems really strange that this is just taken in most books as a kind of postulate, and then things go from there. Although one understands after learning it a bit that it's a strong analogy from what happened with bosons, where there was a minus sign and these things were different, and the Pauli exclusion principle is being held here. So all that is well motivated, but it's worth looking for a story, more story about this. And I'm telling various tales about it from here on out. So one thing you can do is you can, now remember that psi star is this corresponds to antiparticle taking the dagger. And I wrote a 4 here because it makes my normalizations easier. It's usually a 1, just a scalar constant. So I can make the following operators. I can symmetrize by taking psi plus psi dagger, or psi minus psi dagger over I. And in both cases, A dagger is equal to A and B dagger is equal to B. So A and B being equal to their own antiparticles should be Majorana fermions. I'm not making the identification of operator and particle, pardon me. And you can check that A squared is equal to 1 and B squared is equal to 1 on the basis of the commutation relations up here. And that AB, being what it is, will tell you that AB anti-commutes and B anti-commute. So you have a little Clifford algebra. A squared is equal to 1, B squared is equal to 1, AB is equal to minus BA. And so it's natural to associate to Majorana fermions a little Clifford algebra. So each Majorana fermion has square 1, and two of them that are different anti-commute. And then you build fermions by taking A plus IV and A minus IV. The mathematics suggests that electrons are pairs of Majorana fermions. The mathematics suggests, but people have investigated this since papers in the early 2000s by Ivanov and Kutayev, and recent papers and recent experiments by Binacker and other people have shown that it is consistent with experiment to assume that electrons actually are pairs of Majorana fermions. Electrons in nanowires, and they measured correlations between the ends of the nanowires. No one, of course, has seen a Majorana fermion any more than anyone has seen a quark. But nevertheless, this is importantly a part of the structure of an electron. And so that's quite amazing. And I always go backwards. So
a
I
clarification.
can ask, yes.
Are they non-local combinations
Oops.
of Majorana fermions?
I'm sorry. I have this ineptitude with buttons.
Are electrons
There, no.
non-local combinations? populations of Majorana fermions?
Are they local?
Non-local.
Non-local.
Non-local. Well, there's going to, in the case of that experiment, there's a non-locality in the correlation. Perfect. And what it would mean, I mean, surely non-local, I mean, it's a quantum thing that they're bound, but I don't know how to talk about where they are than Majorana fermions. Where are they? Recall, yeah.
Point of clarification, you made a comparison to the structure of the electron and of the quark spectrum, no need to either, but they're both. But with an electron, when you scatter that sucker, behave just like a structureless particle. Whereas when you take a proton and scatter it, even if though you don't see the quark.
Yes, that's right. So this is not so concrete. People worried about whether quarks existed, and then proton-proton scattering experiments show that the proton appears to have substructure.
Right.
I kind of doubt anyone's going to ever see any substructure in an electron.
Right.
It's all going to be external kind of correlations about this subject.
So what do you mean by this being part of the electron structure?
Well, I said it's a mathematical particle, that the electron behaves as though it were two particles, and correlations on the basis of that can be observed, and that's as far as people are going to go. But on the other hand, it doesn't stop us mathematically from wondering what would happen if I had a couple of Majorana fermions of that kind and I move them around one another. Do I get into interesting braiding, which I'll show you I will. And Ivanov had that idea a long time ago, and other such things. And maybe it's too early to tell about the reality of these.
Okay.
Yeah.
No,
Maybe I better go
no.
on because I'm running a little late. So that slide, next slide. So here's a question. Is that Clifford algebra, a squared equals 1, b squared equals 1, ab equals minus ba, fundamental Clifford algebra, is it associated with the mark? Because the mark was our touchstone for a Majorana pattern, right? I want to show you that it is, and that we already talked about it. Consider the process T of x is cross x, negation of x, and its eigenform, which I could think of as a nest of marks, which is left invariant by marking. So there's the version of the square root of -1 at the level of distinction. So remember, that opens up, right? Because we're talking about distinction. That opens up into the wider domain of everything you could ever think about. And at the same time, becomes a very concrete notational form. So we have the clock. And J equals mark implies unmarked, and we have the alternation, and we already talked about it, and the analogy with plus or minus 1, and the eigenform of I, and we're thinking about this process. But now I want to think about it a little more carefully. So the square root of -1 of the clock is the theme. Two ways of looking at it. Let me call them epsilon and epsilon bar, which is minus epsilon, thinking of it as an ordered pair. Conjugate views. But now I want to formalize the time shift that I talked about before in the fable. So I will define eta in the following way. A waveform followed by eta is the same as eta followed by the conjugate waveform. In other words, eta shifted across the AB turns it into BA. Phase shifts it. Okay? So now I equals epsilon eta is time sensitive. If you were to interact with it, you have to interact with eta, which causes a shift in time. And now you multiply I by itself, and you have epsilon eta is epsilon bar, eta squared. Eta squared is about 1 by definition. And then we have minus epsilon, which is 1, minus 1, because of the minus sign. Y squared becomes minus 1. That's the formalization of the sentences in the fable about I being I squared equal minus 1 because of its temporal sensitivity. So on the one hand, there is this process view, and then there is the fact that epsilon and eta generate Clifford algebra. I said our, but it doesn't have to be that one. Here's a Clifford algebra emerging naturally. epsilon squared is 1, eta squared is 1, and eta epsilon plus epsilon A equals 0. The Clifford algebra is the process algebra associated with the self-reference of the mark. So that once you are considering distinction self-reference, which is right there at the beginning, then right there along with it, at least in this description, is the Clifford algebra. Clifford algebra is arising right along with that, and so Clifford algebra is arising right along with that logical particle of the mark. So the fusion algebra and the Clifford algebra are there in that point of view. And what we're looking at when we do this is matrix algebra also. If I can interpret AB plus CD eta, that's one general and 1 and minus 1, as diagonal AB, anti-diagonal CD. The eta is the anti-diagonal. It permutes things. For example, well, you can check that. So you can get matrix algebra out of this, and if you use higher order permutations, then you get all of matrix algebra. But now, in the interest of time, let's leave that and talk about braiding. So I want to think about a row of electrons as a row of Majorana fermions. So I can consider, each electron is 2 Majoranas, but let's just consider a row of Majoranas. Here we have them. And I have Ci squared is Ci, Cj is minus Cj Ci. And I'm going to define AK to be Ck plus 1 Ck. Here's another square root of minus 1. AK squared, you see what happened. Ck plus 1 Ck, Ck plus 1 Ck. Then you permute the two middle ones and you get Ck plus 1 squared, Ck plus 1 squared, and a minus 1 from the switch of the 2 in the middle. So that squares to minus 1. And the AKALs commute when they're far apart. So you have that algebra structure. It's kind of like the quaternions, a lot of square minus 1s, and when they're near one another, they do something, but when they're far away, they commute with one another. Now let sigma k be equal to 1 plus AK over the root 2. And then you can see that they satisfy the braiding relations. These are the braiding relations. If you're not familiar with this, let's go to the diagram. Let me think of a braid. And this is a little braiding of the first two strands that I call sigma 1, and the last strand is left alone. The next one is a braiding of the last two strands, leaving the first strand alone. I call that sigma 2. And I have sigma 1, sigma 2, sigma 1 drawn here, where I multiply braids by tacking them to one another. And you see that topologically, you can take this curve here and slide it down while pushing this crossing up underneath the rope, and you get sigma 2, sigma 1, sigma 2. It's also the case that this is a relation about permutations. Switch these two, switch these two, switch these two is the same as doing it in the other order. And that is seen because you get a permutation of 1, 2, 3 at the top by going all the way down to the bottom. 1 goes to 3, 2 goes to 2, 3 goes to 1. And this is another picture of the same thing. 1 goes to 3, 2 goes to 2, 3 goes to 1. So if you think of this as just a permutation, this is an identity about permutations. But we've added the weaving, and that becomes braiding. And the braid group is sitting over the permutation group in that way, adding extra structure which we can visualize as weaving. And I want to show that these braiding relations hold, and it's easy to see that they commute when they're far apart. So in order to check the braiding relation, you should note that the two adjacent AKs anti-commute, and their squares are minus 1. Now, if you take that equation right there, sorry, this is hard to read, but multiply by AK on both sides, and you get AK plus 1 AK is equal to AK squared is minus 1. The minus 1 goes away. At AK plus 1 AK equals AK plus 1. AK plus 1 AK plus 1 equals AK. It looks like the braiding relation, but not quite. Got a funny term here. Let me simplify this by letting A be AK and B be AK plus 1, and now we can look at it. I have A and B, and and I have A and B anti-commuting, and A squared and B squared are minus 1. So it's still a Clifford situation, it's just minus 1. ABA equals B and BAB equals A. I let sigma A be 1 plus A over root 2, sigma B equal 1 plus B over root 2. Thank you. And I try out the sigma A, sigma B, sigma A. I calculate it. Let's just jump to the end of the calculation. What happens after you calculate it is you get something that's symmetric in A and B. Well, that's what you wanted, because sigma A, sigma B, sigma A equals sigma B, sigma A, sigma B is interchanging A and B in the equation. So the fact that it's symmetric is what we're after. And the way it ends up being symmetric is very simple algebraically. This is as simple as I could make it. I was trying to make it simpler than it was before, and I managed, but for me, but it's still a little bit of algebra. You multiply these two together, you get 1A, B, A, B. 1A and B and AB, right? And then you multiply by 1 plus A, and you get 1 times it, and then you get A times it. A squared is minus 1, BA, ABA, ABA is B. Collect terms, AB and BA cancel, the minus 1 cancels, and you're left with 2A plus 2B. Couldn't be much simpler than that. Thus we see that non-trivial braiding is associated with Clifford algebra. It's right down there in the base of the mathematics. Part of this is a quest of mine. How simple a piece of mathematics can you write that will still have topology in it, okay? So here, it seems a bit unexpected to me that something as basic as a couple of things anti-commuting gives rise to braiding, but it does, it really does, and it's what makes the Majorana fermions have braiding. So let's talk about that a little more. If you took 3 Majorana fermions, you can get the quaternions out of power. This is the A's. BA, CB, AC. And if you check, they all square to minus 1 and IJK equals minus 1. We create the quaternions out of them. And these are the braiding operators for them. And of course, they all commute. They all do braiding just like I said before for the same reason. And then this is Ivanov's idea. Ivanov makes these operators, doesn't even think about the fact that they are braiding themselves, but jumps to something more concrete. He says, take the vector space spanned by, complex vector space spanned by the Majoranas, Hilbert space for the Majoranas, and define operators on it by conjugating by these operators, which by the way can be, never mind, I don't want to go into that, which can be thought of as conjugating these, and then you will see that the following happens. That under that operator, if 2 guys are next to one another in the row, then they get interchanged by the operators if it's the kth operator. They get interchanged with one of them getting a sign, and the other doesn't get a sign. T of x is y, and T of y is minus x. Corresponds to the well-known belt trick, where you take a belt between 2 particles, and you interchange the 2 particles, and the belt gets a 360-degree twist, as I've indicated. But where is that twist associated? In the belt trick, the whole system got a phase change, but in this representation, one of them got the phase change. It's very nice that the algebra of the row of Majorana fermions actually tells you where the phase change occurs, and as a result gives you a representation of the braid group. In this case, the representation is very simple. It's order 2. In the first case, it's order 8 in the one that I originally constructed. I don't know how the one I originally constructed is directly related to the physics or not, but it's surely part of the physics. So if you've got a row of Majorana fermions, then they braid according to this method. So a row of electrons has underneath it this braid group representation. And some people have speculated, as people will, that you could build quantum computers by using that braiding representation, plus something else maybe, allowing yourself to control Majorana fermions. So, of course, this is way beyond us, right? Way beyond anybody, how that you would ever control them and braid them. But you can't stop us from thinking about it. Now I want to show you a side line which is related to this, which is a curious exercise that I found myself doing. This iterant algebra that I've been showing you started talking to me the other day. So let's let A be equal to epsilon eta, that's a square root of minus 1, and B be equal to I eta, another square root of minus 1 because I threw in a commuting I. Throwing in a commuting I is very natural in these situations. You build the split quaternions with the first two, with the simplest Clifford algebra. It doesn't quite have enough I to build the quaternions. And then you go up to the quaternions, usually, by throwing in another I that commutes with everybody, and then you can build quaternions. So this is a couple of quaternions, if you like, or a couple of polys. A squared is minus 1, B squared is minus 1, AB is minus BA. In matrices, I have the representation. A is, that's eta epsilon, right? And B is I eta, there it is. And sigma A is 1 plus that over root 2. Sigma B is 1 plus that over root 2. A familiar matrix. This is the Hadamard matrix. In quantum computing, we call it the Hadamard matrix. It's a square root of negation. And here's another square root of negation. And then these contain I, so it would be natural to get rid of the I. You can get rid of the I by blowing it up into 4x4 matrices. You'd let I be equal to 1 minus 1, 0, 0. And take 1 to be equal to 1, 1, 0, 0. And blow up the 4x4 matrices. And then you get these. This is like the Dirac strip to form Dirac algebra. So sigma A then becomes this. And sigma B becomes this. And these break one another, but, and here's the surprise, I know this matrix. This is what we call the Bell basis change matrix, because each of these looks like a little entangled state in the tensor product, if you think of it on a tensor product. Now I'm talking without telling you the definitions, but we're in a tensor product of 2 qubit spaces in this definition. And each of these vectors is an entangled vector. So this takes the 4 basis vectors in the space to entangled vectors, and it's used in doing teleportation. Well, we noticed, Sam and I, some years ago, in writing a paper about representing quantum computing by braiding operators, we noticed that this satisfies what's called the Yang-Baxter equation. It itself satisfies braiding, where what you do to do that, and I'm sorry to just be telling you this, but there's not a lot of time, is that you run this on 2 lines, so thinking of it as a braiding operator on 2 lines, thinking of them as tensor lines, and then you run it, you also run it on 2 adjacent lines. So you run it on the first 2 lines, leaving the third line alone, or you run it on the second 2 lines, leaving the first line alone, and then the 1 matrix becomes something that braids with itself and satisfies the braiding relation. So, well, this came to me as a curious surprise, because I always wondered, what the heck is this doing there? And now you see there's a nice story about how it occurs. Now, let me come to some conclusions since I'm running out of time. One thing is that I didn't have time to tell you is that, you see, we had this equation, right? And it gives rise to braiding. There's another thing which is directly analogous to it that gives rise to braiding. Look at this. This is called Temperley-Lieb algebra. PQP is P, the outside, not the inside. It's a sort of turned out, inside out version of this. Projectors rather than inverted elements. And again, you get a representation of braiding. And this one is well known to us, and Sam and I have been working with this one for a long time in relation to things like Fibonacci model. And it gives rise to the Jones polynomial, and is all tied up with the topology of the quantum Hall effect. So that was a considerable surprise to me, to see the analogy between these two, and I would talk about it more, but I'm just going to show you 2 pictures and end. One picture is this, that there's a beautiful iconic picture of PQP equals P, if you think of P like that and Q like that. We won't do that. So here's a partial summary. The Majorana fermions are simplest particles. They can be regarded formally as the logical particles. They related to the fusion algebra is related to the Spencer-Brown interactions, and creation and annihilation algebra is related to the Majorana fermions. It's related to temporary beam, and these examples partake of a universality that demands further study. I'm talking about expanding the context to think in terms of eigenform and to think in terms of distinction and cognition in relation to physicality. And one final suggestion, maybe we would understand the quantum Hall effect better if we thought of the collectivities of electrons in it as collectivities of Majorana fermions, letting each electron do things. I'll stop.
We've had a lot of questions during the lecture. I think we haven't got time for more than one question.
Yeah, we want to make time for Sam, so.
Yeah, we want to make time for some. Just one question. Anybody not asked a question before?
I've had questions.
I don't know if mine is not a question. No,
No, she's had a few questions. So
Okay.
I was asking.
I'll ask one. In my theory, you cannot take the observer or the observed out of the observer or vice versa. You know, it's physically impossible as a primary.
Yeah, I
Now,
think
in
I
this
say-
situation, it would say
I say the
you
same.
can't take, just in this situation, it would say you can't take a mathematician out of mathematics. If you include the mathematician as the entity that is doing the mathematics, and look at the physical result of that, I think you would get the result that you're talking about. You know, the sum of plus minus done by a mathematician is an oscillation.
Sure, where the mathematician could be
A
a
computer.
much larger system than the one you think you're talking about.
Right.
And you can't put any limitations on it, I think of some small, right?
Right.
Yeah.
Sure. It's a general thought, it's a mechanism. Yeah.
Right.
Okay, can we just close down the discussion and continue to over the coffee? Can I ask the next speaker to come forward? Sam Monaco.
Oh, I just want to make a gentleman. I may